And so what I want to do now is the rest of the talk is just talk about some metallurgical modifications to control crack nucleation. And this is where the ferrous metallurgy comes in. And so we're going to look at a couple of different examples. And the first one is on one operation that we did at Mines in our Steel Research Center in terms of enhancing the fatigue performance of steels for crankshafts. And so what I show you here is the desire here is to develop materials, high-strength steels that facilitate lightweight designs in advanced power transmission systems, such as crankshafts, bearings, other gears, anything that transmits power. So here's a crankshaft, and we see one journal in a crankshaft and FEM model that shows you the high stress zone at the fillet. And so what we did is we designed that specimen you saw the failure of a minute ago as our deep rolling sample to simulate the fillet in a crankshaft. And so what we did is subjected this sample to a process called deep rolling. And what is deep rolling? This is deep rolling. Deep rolling is where you can take that sample and impress into the surface a roller with a ground geometry that matches the fillet that you're trying to put it into. And while you're pushing on it, rotate it multiple times, and what you'll end up with doing is locally altering the surface of the material. It's a process called deep rolling. For those of you who haven't seen this, you certainly are aware of shot peening, which is a process that also does some of the features here, but not all of them. So you'll get a schematic now of what's happening into the deformation zone. You get a local zone right below the notch where you actually plastically work the material and you increase the strength. You generate this radial non-symmetric strain, so that means that you've imposed a gradient in strain, which means you get a residual stress. And the mechanical process burnishes the surface, making it smoother. And the combination of those, increased residual compressive stress, smoother surface, increase the surface strength, are all things that are increase the fatigue life, most of which we knew from Wöhler's work in the mid-1800s. And so the trick here is the residual stress, and the ability for it to really perform, it depends on the stability of the residual stress, because one way you can get rid of a residual stress is by plastic work. And so you need something to stabilize the residual stress. Well, let's look at some data. How effective is this? Here is a SN curve for, I took one of our various steels we tested. This is 4140 steel. Quenched and tempered, heavily tempered, so it's 30 Rockwell C. And here's an SN curve of the as received bar at 30 Rockwell C. Just deep rolling, you can take and increase the endurance limit by 50 to 60%. Which is a particularly significant increase in its fatigue life. And what we did is we hypothesized that you could do this more if you did deep rolling at a condition where you could stabilize the dislocation structure that was responsible for maintaining the residual stress. And so if we could stabilize that dislocation structure, we could improve the fatigue resistance. We suggest there are two ways you could do this. One is age, use strain aging and age a previously deformed sample. And the second is form under dynamic strain aging. And it's the latter that I'll show you some examples of. So we go back to some classic work of Lee and Leslie in the 1970s, where they did some work on low carbon steels. This is just a family of stress strain curves of low carbon steel at different temperatures. And the purpose to show you this is what happens to the material flow behavior in a dynamic strain aging range. That's the range where you see cyclic peaks and valleys in the stress strain curve between about 150 and 250 degrees C. And you'll see two things happen. The strength goes up quickly and the work hardening rate goes up quickly. And this is hypothesized that solute pins the dislocations, you get an increase in dislocation density, and you change the structure from a cellular to tangles, and possibly the combinations of all those give you a structure that may be more stably against mechanical response. So this is what we did. After then deep rolling a material, we surface heated the materials to 340, and then they cool slightly during deep rolling. But look at the increase in the endurance limit just by taking that material and imposing a relatively inexpensive heat treatment, a couple of hundred degrees, and we've now increased over the baseline the fatigue limit by 100%. So here's the crack nucleation more difficult. That's why we've increased it, because if you notice that all these curves tend to go together at high strain amplitudes, where low cycle, high strain, because the plasticity is going to eliminate what you put in there. And so there's an example of how you can use simple metallurgy to really increase or improve properties of materials. And I think there are other opportunities. I'll show you two other examples very quickly related to power transmission systems, and that's the effect of alloy content. And so our interest here is really in gears and bearings. And gears and bearings, gears particularly subjected to two different types of loading. Either you get contact stress or you get contact fatigue. You see that in bearings as well as in gear faces. Or you get bending fatigue, as such as you see at the root of the gear tooth there. And I'll show you some results briefly from both of those. For rolling contact work, this is some work that came out of Timken. And on the left-hand side, upper left-hand corner, is a schematic drawing that shows a bearing rolling on a flat surface and the Hertzian stress distribution that develops below that. As a consequence of Hertzian stresses in the red box zone, you'll develop subsurface cracks, as shown in the middle micrograph on the left, where the subsurface cracks have to nucleate at something, and that's usually an inclusion. And as a consequence of the subsurface crack in the lower left-hand corner, you see what results in a spall. And once the spall comes out, now you have noise in your bearings, and you know that you have a problem. Well, you look at what Timken has done, and what the steel industry has done to improve this is going from 1980 on the right-hand side to today on the left, the upper red horizontal, simply says making cleaner steel. And the x-axis is a measure of inclusion content via the total inclusion stringers. And the net result is you see the fatigue life of bearings is approaching 10 to the 9th, where you can do conventional steels are approaching the fatigue life of vacuum arc remelted steel. If we all relied on vacuum arc remelted steel for the bearings in our automobile shafts and transmissions, we couldn't afford our automobiles shafts and transmissions. And so this is really significant, and it really points out something that you can do. A second briefly is, George Crouch and I have done over the years a lot of work on bending fatigue, where we took one of those fatigue samples that we designed for the laboratory to simulate root bending fatigue. And we observed that in these materials, these are carburized samples, and at the surface you get intergranular crack nucleation associated with the growth nucleation of fatigue crack. And that intergranular nucleation, which is shown inside that red arrow and is that gray schematic on the right, tends to grow by stable fatigue crack growth up to a critical value, and then you get an unstable overload. And so the question is, there's two things that you need to do. Is you need to suppress this type of a process, but then industry is also trying to move to more efficient production operations, one of which is to move to higher temperature plasma or vacuum carburizing, where the higher temperature process temperatures greatly decrease the time for heat treating. And if you could decrease the time for heat treating, you can make parts much more efficiently. So our particular study was to look at how do you stabilize microstructures and let you take samples and heat treat them at higher temperatures. And so typical vacuum carburizing might be at 950 C. These are samples that were carburized at 1050 C, significantly shorter time. And we went through a study and showed that you could do, through appropriate niobium additions, use niobium to suppress grain growth. And on the left-hand side, you'll see three different microstructures, O2, O6, and 0.1 niobium. And at the O2, at the 1050 centigrade, we got unstable abnormal grain growth. Well, that abnormal grain growth led to a very, very low performance and low fatigue lives And you can see there on the right the significant improvement of fatigue obtained simply by controlling locally the nucleation phenomena in this material.